All right, guys. We're running a little bit late. We'll go ahead and get started. My name is Jason Hale. I'm here to share a little bit about investigating malware using registry forensics. So just a quick background on myself. I work at a company called OneSource Discovery. We're a digital forensics consulting firm based here in Louisville. So I've worked there for the past 9 years or so. I primarily focus in cases ranging from intellectual property theft to patent infringement, copyrights, contract disputes, malware investigations, incident response, kind of that whole realm. Been there for the past 9 years or so. I'm also doing a little bit of adjunct instructing at U of L, so see a couple of my former students in here. Good to see you guys. So we'll get started. So I don't know how many of you have worked with the registry too much. How many of you have some experience messing with the registry to any level? So about half or so of you. So we'll go into a brief intro of the registry just to make sure everyone's on the same playing field when we get into some of the actual artifacts that we'll talk about. So we'll talk about why the registry is important. We'll talk about what it is and kind of some of the nomenclature and terminology so that everyone's on a equal ground. And then we'll get into specifically some of the detection, persistence, investigative methods that can be used specifically in the context of a malware investigation. All right, so I just want to preface this by saying when you are doing a malware investigation, obviously there are parts outside of the registry, the file system and other locations that are going to be critically important, but this presentation is not suggesting that you only use the registry. I'm just trying to highlight how important it is and the value of the information that you can grab from the registry if you're only looking at that. Okay, so why is it important? Well, the high-level view here is that there's a ton of information stored in the registry. Everything from system installed services, installed applications, program execution artifacts, user activity, essentially everything that Windows wants to keep and maintain to enhance the user experience or to maintain a history of certain things that are happening. A lot of that is stored in the registry. And it's interesting if you take a look at the value of the registry relative to kind of some of the other information on the disk in the context of an investigation. You may have a couple hundred megabytes that comprise the entire registry of a system. So if you think of a couple hundred megabytes as compared to a terabyte of information or more on an actual disk, the value of that information that you get from that 200 megabytes of investigating that data is really pretty incredible compared to essentially everything else in the file system. Okay, and obviously registry forensics is important outside of malware investigation. So most any type of analysis you would be doing on a Windows system, you're probably going to want to dig into the registry. Okay, so I think this was pulled from Microsoft. I'm not exactly sure where I'd grabbed this, but this is just a generic kind of description of the registry. Basically, most of the stuff I've already covered. It's a central database used to store system configuration. And again, the idea here is that we're trying to enhance the user experience. So there's a lot of things stored here that relate to history of execution, history of file access, and so on. Which to the user they may not care about, but from the forensic side, from the investigation side, is very important and useful information. So this nice little graphic here just kind of shows the progression of the registry all the way from Windows 3.1 to Windows 10. So you can see, with the exception of 3.1, it has, from a visual standpoint, from a regedit standpoint, it has basically remained the same. And in fact, if you got down to the binary level, the actual structure of the registry hasn't really changed. So you can use the same registry tools that you used for Windows XP for Windows 10. For the most part, you're going to be able to see anything that you would be able to see with the latest and greatest tool. So you may have certain information that is moved from one location to another, or certain information added in the Windows 10 registry and removed and so on. But for the most part, from a binary level, it has remained the same. All right, so just to go over some quick terminology here so that way everything kind of makes sense as we're talking about it throughout. The registry essentially is composed of keys, subkeys, and values. So you can kind of equate that to the idea of folders, subfolders, and files in a file system. Okay, so a registry key may contain either subkeys or values. Registry keys are unique in that they will also contain a last write time, and this can be equated to a last modify time. Okay, so we don't have the creation time, we don't have access time, we don't have those typical file system timestamps that we would normally see, but with the registry, we do have a last modify time. Okay, so that will help tell us things like when is the last time that something changed with this particular registry key. Okay, so we don't necessarily know what that change is. It could be a value added, a value removed, something updated. But if we know how that particular key is updated and the frequency and the types of events that update that registry key or the values within that key, then we can make some inferences as to what that last write time actually is. So is that the time when this particular file was accessed, or what does that last write time equate to? Okay, so outside of the keys and subkeys, you've got values. And values are essentially, if you think of from a development standpoint, if you're declaring a variable, you've got a value type or variable type. You've got the name, so something that's going to be used to delineate what that is in the actual content, so the value data. You can see the value type. It can range anywhere from a DWORD or a 4-byte value in this case to a string or to a binary blob. And we'll take a look at some of those binary blobs here in a little bit. All right, so when you look at the registry in regedit, so if you just go to run or type in regedit in the search bar in Windows 10, it'll bring up something that looks similar to this screenshot here. And as we saw in the previous couple of slides, it has looked the same for several years now. But what's happening here is Windows is doing a lot of aggregation and a lot of work for you in the background. And it's actually combining information from multiple files on disk called registry hives. Okay, and so the primary hives that comprise the registry as we see it in regedit are these 6 listed here. And if you were to draw a line between these 6, you would want to do it right here between security and NT user. And the reason is these top 4, the software system, SAM, and security, these are all located in the system32 config directory, which means that they are central to the entire system. That means the information within these registry hives aren't necessarily associated with a particular user account. We can't say that because this information is in the software hive, we know that this particular user account performed that action without further investigation. Okay, so these are all central to the system. You only have one active copy that's excluding other backups and other things that you would find. The last 2 here, the NT user and user class.dat, these are unique to each user account. So each user account in the system will have their own NT user hive and have their own user class.dat hive. And the reason this is important is because we can take the information that we find in those registry hives and we can associate it with a particular user account. So because we found this information in the NT user hive, we know that that is associated with this user account. And the same goes for the user class.dat. Okay, so there are 3 primary questions that the registry analysis can help answer in the context of a malware investigation. And the first is, did it execute? Okay, so that is, did malware or something suspicious maybe we don't know about yet execute on the system? Okay, and so we'll look at quite a bit today, some program execution artifacts that remain in the registry that can be leveraged in the context of a malware investigation. In fact, that's where we'll spend the majority of the time today. But it can also help, the registry analysis can also help to answer how is persistence maintained? Or in other words, how is the malware, how is the attacker maintaining a foothold in your network or on your system? Now, that can span well beyond the registry, but the registry is one specific component of the operating system that's often exploited in the context of persistence. And then finally, what files and folders were accessed? Now, obviously, this is most any type of investigation, you may be interested in files and folders accessed, but that's also important in malware. So we'll look at that as well. All right, so the first location that we're going to look at with regard to program execution is one that's been around for a while. It's called MUI cache or movie cache. This is located in a user hive. Okay, so either the user class or NT user, depending on how new your operating system is. Most anything you would look at now would be user class. So since we can attribute this to a user account, we know at least the context under which this particular executable would have been run. Okay, so what we'll find in this particular registry key are things like the path to the executables launched. We'll find, importantly, executables that were launched from the command line. So this is something that separates MUI cache from some of the other artifacts that we'll talk about that require shell interaction. So in the MUI cache, you may actually see files that were executed from the command line. Unfortunately, we don't have a program execution time. So we can look at this and say, okay, we know that these particular programs were launched, but we don't necessarily know when they were launched without further investigation into other locations. So if you were to take a look at this, this is a screenshot from a forensic viewer here. You can see here the actual value name. This is located in the MUI cache. The value name is just going to be the path to the executable. And what's neat here is that in the value data, you actually have the description field of the exe. So this is internal metadata from the exe that's written into the registry. So typically it's the description field. In more recent versions of Windows 10, you'll also see the company name. So in some cases you have both of those components located in the MUI cache. And since this description is pulled directly from the executable, you can pick up on some pretty cool things that may be going on. So if you look here at the third from the bottom process, you've got a description called execute processes remotely. Does anyone recognize that description possibly from an executable? It is a sysinternals tool. Yes. PSExec. So you can see what happened here is the actual PSExec executable is just renamed to pe.exe, but when it was run, the description from PSExec, because it was a valid executable, was pulled in and saved there in the registry. And you can see this is an actual, just looking at the properties of PSExec, we can see sure enough the description there is execute processes remotely. Okay, so app compat cache. This is a pretty big one in terms of program execution. This is a value in the registry in the system hive, so it's global to the system, and it's associated with the Windows Application Compatibility Database. Essentially, you can do a bunch of research on that, but the idea behind this is exactly what it sounds like. It's trying to make sure Windows is trying to make sure that the executables on your system are at least moderately compatible with your system, and they're not going to crash it, they're not going to cause serious issues. But the way that presents itself, and the reason that is important in the context of a forensic investigation, is that information about these executables is actually saved in a large registry value called app compat cache. Okay, so you've got located in this actual registry value, you can see this is in regedit, there's a single value, but you have things like the file name, the full path to the executable, and a timestamp of that executable as well. If you were to look here in regedit, you can see just by this scroll bar, maybe kind of hard to see, but there's a ton of information here. Not exactly user-friendly to parse. Luckily, there are plenty of tools out there. Well, there are tools out there that do this. The one I'm using here is Registry Explorer. It's a free tool. If you're looking at the registry, it's a great one to use. This parses this automatically. So I'll just look at the app compat cache value here. It's going to parse out these values, and I'm applying a filter in this case to just everything in the temp directory. So what this is showing me are executables in a temp directory somewhere, as well as a timestamp. Now, the important thing with this timestamp is that, with the exception of older versions of Windows, this is going to be the last modified time of the executable, not an execution time. So that's a very commonly misunderstood artifact or timestamp, because people, when they look at this, they want to say, okay, this timestamp, this must be the last time that program was executed. In reality, that's probably not the case unless you're looking at an older system. And in fact, if you have executables that are time-stomped, I mean, you're just looking at the time-stomped value here. So it's not even, may not be valuable at all, other than the fact that you can see that this executable existed at some point. I mentioned, or I had a bullet in a couple slides ago about the app-to-pack cache only being written to the registry at shutdown. And that's important because if you go into a live scene and you just pull the registry hives off the disk, or you do a live image, you are getting those registry hives as they exist on the disk. You're not necessarily getting all the cache information that hasn't actually been written to the registry yet. So in order to get that, you would need to do a memory capture on site, or if you've got a system that had been shut down previously, you would have this. But the key here is that you could end up with a lot of information in RAM associated with the app-to-pack cache that is not available in the registry until shutdown, unless you grab a memory dump. Luckily, if you do grab a memory dump, there's a volatility plugin. So volatility is one of the there's kind of two, maybe three big memory analysis frameworks. Volatility is one of those. It has a shim cache plugin. So you also, if you're doing research on this and you see the word shim cache, that's essentially that's app-to-pack cache. So they're kind of loosely the same words are used for the same thing there. Different words are used for the same thing. But there's a shim cache plugin, and so you can run that and filter. In this case, I'm looking for executables in the app data directory. So anyway, it's important to understand that you may be missing quite a bit of information if you don't grab a memory dump when you're looking at this. All right. The mCache is another part of the application compatibility database. So just like the app-to-pack cache, this is also associated with that same feature. However, unlike the app-to-pack cache, this is an entire registry hive all to itself. So I didn't list it in the primary hives in the beginning of the presentation, but you can actually load this thing up into a registry viewer and look at it just like you would any other registry hive. And this stores a ton of information about programs and DLLs and executables on the system. Okay, so everything from hash values, multiple timestamps, metadata about the executables, kind of like we saw in the MUI cache, file sizes, all of that is going to be stored in this mCache. So technically it was released with recent versions of Windows. However, if you're going back to Windows 7, I don't remember offhand what update it was, but there's an update released for Windows 7, and as long as you've installed that, the mCache is going to be backported onto your Windows 7 system as well. So even if you're looking at older systems, you could very well run into this artifact. So if you were to take a look at this in a registry viewer, this is again using that Registry Explorer tool I talked about earlier. You can see that there is a programs key with a bunch of subkeys that appear to be randomly named. Within each of these subkeys, you have quite a bit of information about a particular program on that system. So in this case, we're looking at a TrueCrypt version here. And if you look at the value names, you can see it's 0, 1, 13, 14, not exactly descriptive, right? So we can see by the data, okay, maybe this is the product name, maybe this is the version, but some of this other stuff, we don't know what it is. Luckily, that's been documented. So a lot of this, we can kind of figure out what those particular values are associated with. So you can see at the top, we've got the SHA-1 hash. So that would allow us to do whitelisting, blacklisting, and looking for other instances of this particular program across an enterprise. And this is all, keep in mind, this is all without access to the actual program or the executable itself. So this is based solely on information in the registry where that file was stored or executed. You've got a few timestamps associated with the executable. So the file system modified time as well as the creation time. So this is the file system timestamps. You've got the compile time of the exe. So this is some of that internal metadata as well as the product name. So what's kind of cool here is that if you combine the data from the mCache, specifically the product name and the compile time with the MUI cache, you could potentially build a decent profile of an executable from an internal metadata standpoint. In other words, you know when this executable is compiled, you know the product name behind it, you know the company name behind it, and you know the description, at least based on the internal metadata of the exe, all without actually having access to that file. So all just with information stored natively in the registry. Any questions? Cool. And actually, one more thing I forgot to mention with respect to Amcache. One of the really neat things that this allows you to do that kind of sets this apart from other artifacts is it allows you to determine executables that arrived on your system as a result of program installation. So, for example, when you install Microsoft Office or any large application like that, there are going to be multiple executables dumped on your system. Well, looking at the Amcache and doing analysis of that will allow you to determine which executables exist on your system as a result of some type of MSI installation or some type of installer versus which ones do you not know how they got there, right? So we don't know whether they were downloaded. Maybe they're in the, they're in some random directory. We don't know why they're on your system. So if you can take those handful of executables that we have no idea what program they're associated with or how they came to be on your system, you can dramatically reduce the amount of data you're looking at and the time that it takes you to analyze that system. All right. So user assist is another location here that we commonly look at with regard to program execution. This is different from some of the others in that this will require interaction with the shell. Okay, so this is not going to catch users running command prompt or executing commands from the command prompt. It is going to require interaction with the shell, so it's kind of a caveat here. However, if there is shell interaction, you're going to find some pretty valuable information here as far as program execution, the last time programs were launched, the context of the launch. So because these are in this is in a into-user registry hive, you can tie that to a specific user account. So we know this user ran this particular application, and here's the last time they ran it. Okay. If you were to look at these in regedit, you would see some garbage that looks like this because these values in the user assist are ROT13 encrypted. Okay, so if you needed to decrypt those, you would just shift each letter in that value down 13 letters down the alphabet. Are you familiar with ROT13? So very, very trivial to decrypt, just kind of annoying if you're trying to look at it in regedit. But most any forensic tool or any user assist viewing tool will decrypt this for you and show. So if we're looking here, you can actually see, here's an example. You can see in this case, there's actually, looks like a benign executable, but it's showing an executable being launched from a network resource. So you can see there's a controller resource here that's being accessed, and there's an exe being launched from that. We can see the number of times that particular exe has been launched, as well as the last time that it's been launched. Okay, so you can use this run counter in things like the least frequency of occurrence analysis. So if you find that most applications on a system have been run at least a dozen times, maybe even a few hundred, depending on what they are, but then all of a sudden there's a couple of them that have only been run once or twice. Well, if you look at those a little bit closer, you may find that they could have been a dropper, it could have been some of the initial infection points, all just through looking at the run counter or the number of times it's actually been executed. All right. So recent apps, this is the last program execution artifact we'll look at. This is new to Windows 10. And as far as I know, it is currently undocumented, unpublished. So if you're looking into it, you heard it here first. This will track actual executed programs as well as files accessed from those programs. So it kind of combines a few different investigative techniques all into one location, located in the into-user hive. And you can see here, I'm looking at an example of command.exe being run. You can see the last access time. Okay, so this is stored as an 8-byte value. It's a file time format, so it's a pretty standard NTFS file system time. So you can easily convert that if you have the right tools. And then you can see a launch count. Okay, so if you're looking at this, since we just talked about user assist, you may be thinking, well, this looks like the same type of information that's in the user assist key, right? So you've got the path to the executable, the number of times it was run, the last time that it was run. And in fact, in my experience and my research, I found that it is the same, right? So these numbers, these statistics will match what's in the user assist. The reason, however, this is also important is the user assist is one of the most well-known locations for storing executed user activity in general, right? So you can generalize that. So if you have any type of anti-forensic measures being taken, whether that's from a user standpoint of intentionally clearing information, or that's from the system doing some type of cleanup, you can pretty much bet that the user assist is going to be one of the first locations in the registry that's going to be wiped out from an anti-forensic standpoint. However, things like the recent apps and some of the lesser known locations, these may not be wiped out because they're not known about, right? So you have to know about these locations before you can get rid of them. Okay, so finding additional locations of information like this will allow you to not only uncover things that may have been wiped out from other locations, but it can also help you increase your overall confidence in your findings. So if you've got 3 different things showing that an executable has been launched, and here's the last time it's been launched, you're probably going to be more confident in that finding as opposed to if you only found that in one location. Okay, so let's talk persistence for a minute. Now this is a pretty expansive topic. I think there's a DerbyCon presentation focused on persistence. There's plenty out there. This expands well beyond the registry, so we're not talking about just looking at registry keys and values when we look at this, but the registry is certainly one of the most prevalent locations with regard to persistence. And what we're talking about, just to clarify here, is how is an attacker, how is malware surviving reboots or surviving these events that would normally take care of them, that would normally wipe them out. Okay, so some of the locations in the registry that are important here, the run keys is a big one. This is a very well-known persistence mechanism. They're called run keys in the software hive and into user hives. Essentially, they dictate programs that will launch whenever the system either starts or when a particular user account logs in. Okay, so this is one of the first locations that would be checked by either any type of antivirus program or an analyst on the back end looking for persistence mechanisms. So very well-known location. I don't have a screenshot of that, but image file execution options. This is another one that's interesting. If any of you are familiar with the sticky keys attack, this more recent versions of that leverage the image file execution options. Another legitimate use of this is, how many of you use Process Explorer? Does anyone use that? There's an option in Process Explorer to replace Task Manager with Process Explorer so that when you press Control-Delete and go to Task Manager, we'll actually open Process Explorer instead. Well, what that's doing, what Process Explorer is actually doing there is setting a debugger value in the image file execution options key to say, hey, whenever if this was Task Manager, whenever Task Manager is invoked, what I actually want you to do is I want you to run Process Explorer. Okay, so in this context, I mean, that's a legitimate instance of that, but you can see how this could easily be abused. If you've got a program that is monitoring for when a particular application is started, we'll say Excel is one. Whenever Excel.exe is called, what I want you to do is actually launch this executable. That executable will run in the background and then turn around and start Excel.exe. So from the user standpoint, that's all transparent. The user sees nothing different. They click Excel and Excel starts up. But in the background, there's other processes being started, or at least one, all transparent to the user. Okay, just the idea of application hijacking is another big one with regard to persistence. And this is kind of just a general concept, not necessarily a particular key, but what we're doing here is we're looking for specific events that could be Bluetooth connections, Wi-Fi connections, specific functions, or DLLs being called. Whenever that happens, we want to inject our code that we want to run. We'll run our code whenever that targeted action occurs. We'll preserve the original action, just kind of like we saw in the image file execution options. And then once we have our DLL, or once we have our code running, we'll then turn around and launch whatever the user would have expected. Okay, so an example of this would be things like If you've got some type of downloading program, a torrent, that is set to scan any files that are downloaded from the internet when they're complete. Typically in those types of programs, you can provide the path to an antivirus program that you want to use to scan that. Well, there's nothing preventing you or an attacker from, instead of replacing that antivirus path with a path to an executable that they want to launch whenever a program is downloaded. So the program is downloaded, their executable is launched, they then turn around, launch whatever antivirus was expected, and they scan the file and you go on. Okay, so obviously instances like that are more targeted, but they're just that's an illustration of how prevalent and how easy persistence really is to maintain. And this is just looking at the registry. There are plenty of our instances outside of this that are even more interesting. The Hexacorn blog, hexacorn.com, has a great series. I think he's up to like 60-something blog posts on. It's called Beyond the Good Old Run series, but it is it's a series on some of these exotic persistence mechanisms, like using this antivirus when a program is downloaded to remain persistent on a system. So if you're interested, take a look at that. And just kind of looking at some more interesting uses of the registry and how the registry is presented here. How many of you have heard of the Unicode right-to-left override character? Anybody? So a couple of you. If you've done any type of work with code sets or anything, you may have seen this, but generally you probably haven't heard of it. So this is a simple way for malware, for anything, to hide in plain sight in the registry. So the way the right-to-left override character works is it takes everything after the RLO character and it reverses it. So, for example, you can do this easily in regedit. If you were to create a key, insert the Unicode control character, and then insert the right-to-left override, and then type in TFO SOR CIM. So you got the right-to-left override. You type in Microsoft spelled backwards. When that registry viewer interprets that, because it understands Unicode, it's going to see that right-to-left override, and it's going to reverse that so that whenever you're looking at it in regedit or any Unicode-capable registry viewer, it's just going to look like Microsoft. And you can obviously replace Microsoft with anything you want to call it, and you can store this anywhere. So this can be deeply embedded in the registry where it's not exactly easy to find. Okay, so you can see how this could be easily leveraged for malicious purposes to store either configuration files, which we'll talk about here in a second, or just hide data that you don't want to be obviously visible. So, we've seen instances where registry keys will be randomly named or other things that kind of stick out if you're just looking at it. But using things like the RLO character can allow you to name something that looks legitimate, but is actually something completely different. Okay, so if you look at this, is looking at it in an actual registry, forensic registry viewing tool. Because this understands Unicode, you can see that it's just displayed as Microsoft. So nothing looks different visually. It's not until you actually inspect the hex of that particular registry key that you see, oh, there's an RLO character followed by Microsoft spelled backwards. Well, obviously, you're probably not going to be doing that to every registry key that you see. So it's very easy to blow right past this. Just an analyst tip here. There's a great there's a Redripper plugin. If anyone has used Redripper, it's a good great tool for registry analysis, quickly pulling important information out of multiple hives or a single hive. There's a Redripper plugin to pull out specific paths that contain the RLO control character. So that's a great one to use if you're looking for this specific type of thing here. Oops. Okay, so the other kind of interesting concept within the registry that I want to talk about here is the idea of large registry values. Okay, so this is often utilized for things like generally persistence and execution, but specifically storing scripts, so storing JavaScript, storing configuration files, within an actual registry value. Okay, so there's nothing necessarily keeping us from storing a couple kilobytes or more data within an actual registry value. And we saw that within the app compat cache key when we looked at that. So, or app compat cache value, excuse me. When we looked at that, we saw there was a ton of information there. And that's a legitimate use of a large registry value. But there's nothing preventing us from, instead of storing all that app compat cache data, from storing, say, JavaScript or storing configuration data associated with the malware installation we have or what have you. And we see this particularly with fileless malware. So when you read a lot about that, a lot of the time it's utilizing these large registry values to store its information. So it's all embedded there. You can see in this case you've got, this is I believe from Polix. So this is actually some JavaScript or encoded data stored right there in the registry value. Okay, so you can, this is pretty easy to see how it can be leveraged for malicious purposes. And particularly when you combine that with the RLO character, you can see how those two could be used to hide quite a bit of information there. Okay, so just kind of wrapping up here. On the investigation side, this could easily be an entire presentation to itself. So I kind of picked one artifact that I thought if you have this artifact, then this is one of the better ones to analyze in the context of an investigation, and that's shell bags. Now the biggest caveat here is that this is going to require interaction with the shell, but to the extent that that the attacker has that level of access, the amount of data in shell bags is pretty significant. So shell bags kind of came around when, if you've ever resized a directory, moved it from one screen to another, and closed it, and then maybe reopened that same directory a few days later, and you notice that it opened to the exact same location with the exact same dimensions. Anyone notice that? So what's happening there is shell bags are maintaining that information, that positional and sizing information of that specific directory you had opened. It's maintaining that in the registry. So we don't care necessarily as much about the sizing and position, but it's the other information that shell bags store that we care about. Okay, so things like the modified access and creation times of those directories that were interacted with, which can allow you to, or shell bags can allow you to determine the structure of volumes that have been accessed from the system. These could be volumes across the network. They could be even zip files that are explored by double-clicking it. So if you think of anything that you can explore in Windows Explorer by double-clicking it, these would show up in shell bags. Okay, so FTP sites. This is another one. If you looked at it in regedit, it would not be fun to decipher. You can see it's a highly nested structure. All of these are just, all of these values are binary blobs. Each of these have nested data structures. Not fun. You wouldn't want to do this by hand. So luckily, there's a great tool called Shellbags Explorer that I would encourage you to download, if nothing else, just to look at on your own system. So this will obviously you can feed in a registry. It's a USR class hive. You can feed that directly into Shellbags Explorer, or you can open up your live system and take a look at it there. But what this will show you is it will reconstruct a good portion of the directories that have been interacted with on your system. And this is pretty much for the lifetime of your system. So maybe that directory that you forgot you looked at like 3 years ago or 4 years ago, if you look at your own system, it's probably going to show up here. And it's really pretty incredible the amount of information that you find in shellbags, particularly on a system that's utilized pretty heavily. But you can see in this case we've got a few different volumes that have been explored, a C drive, obviously a P drive. And then if you look a little bit further down, you can see an actual, that network resource we looked at earlier, the controller. You can see there somewhere the control panel. So if you were going in and changing different things within control panel applets, that would also show up in shellbags. All of this would also contain information like, may contain information like the first time you interacted with that directory and the last time. Okay, so we can utilize those timestamps to see what was being accessed and when from a directory standpoint. And you can even see that there's specific information about the MFT or master file table record number. So file system specific information about this particular folder, so that we can see that, okay, this was clearly an NTFS file system that was being accessed. This was a FAT file system, or what have you. So a ton of information in shell bags available to us. Just some other locations I've got listed here. I'm not going to cover these just from a time standpoint, but these are other locations you want to look at. So just kind of wrap up here. The three primary locations that Registry can greatly help in with malware are program execution, persistence, and activity. We focused today on program execution, looking at app-to-pat cache, M-cache, which isn't listed here, MUI, user assist, recent apps. All of those can help illustrate or build a picture of what has been executed on the system, when was it executed, what programs may have existed, and so on. And keep in mind here that when we talk about program execution, when we talk about activity and persistence, this is all regardless of whether or not that executable or that file actually exists on disk. So that file could be on there for a matter of seconds. As long as it's executed, it's going to show up here, and then it could be wiped out later. We don't necessarily, I mean, that would be nice to have that, but we don't necessarily need that executable in order to build this picture. So we saw through, for example, MUI cache and AM cache, that you can build a decent profile of an executable from an internal metadata standpoint just by the data stored in those registry keys and values. So that's all I got for you guys. If you have any questions, I think I've got a couple of minutes, kind of right on time, but feel free to ask me. Yes. Yes, yeah. So the question was, is there any way to search the registry for a given time frame if you know the specific window that you're looking at? And the answer is yes, to an extent. So Registry Explorer, the program we were looking at earlier, and plenty of others have a date filter where you can put in, okay, show me everything with the last write time between, you know, this minute and this minute, and it will show that to you. The only thing I would caution you on is there are certain things like the user assist, like the recent apps that we looked about, that contain embedded timestamps that are in binary format that wouldn't necessarily show up in that particular search. But if you were just to look at the last write times and want to timeline that, yes, and Registry Explorer is a great one for that. And that's free. Yes. Yes. Yeah. Yeah. The question was, will auto runs catch image file execution options? And yes, it will. And auto runs will catch a good portion of these. So if you're running auto runs from sysinternals, that will catch a good portion of the persistence mechanisms. Not necessarily some of the more exotic ones, but the run keys, your typical ones, your image file execution options, the stub path keys, which I didn't really talk about. Auto run should catch all of that. All right. Thanks, guys.